Hi, my name is Mahmoud Al-Nasri. I'm a pavement design manager with Tarmac. This presentation is about polymer modified bitumens. Due to the increasing number of commercial vehicles and axle loadings on the roads, there has been an increasing demand for more durable, better performance road pavements. Certain locations within the road network require special attention: roundabouts with high stresses applied, and low maintenance frequency areas to minimize traffic disruption. Polymer modified bitumen can offer solutions to these challenges. To start with, asphalt mixture is the most common road used material for construction of the roads. It consists of bitumen, aggregates, filler, which are less than 63 micron in size, and air voids. Different proportions of these components generate different types of asphalt mixtures. So how does the asphalt mixture or the road pavements fail? Road pavement does not last forever, but gradually deteriorate. The most common pavement deterioration mechanisms are cracking and permanent deformation or rotting. Cracking, which can appear on the top, is usually appears on thick pavements due to the environmental hardening known as oxidation to the bitumen on the surface. This type of cracking from the top is to the bottom known as the top-down cracking. The second type of cracking is the bottom-up cracking, usually occurs in thinner pavement due to tensile loading stresses from the vehicle's loading. The second type of deterioration mechanism in the asphalt pavement is rotting, or known as permanent deformation. It occurs due to the repeated loaded application from the vehicles. It can show up only limited within the surface layer, known as the non-structural rotting, or it can extend to the lower layers, known as structural rotting. But why cracking and rotting occur in the pavement or the asphalt material? If we have an elastic material and we applied a load for a time, the material will instantaneously respond to the loading and extend or deform. If you remove the loading, it will go back to its initial position, i.e., the deformation will go, or the strain. This is by definition the elastic material. If we look on the graph, if you can represent this by a graph, if on the top one, if we apply loading from time t1 to t2, the material at time t1 will instantaneously respond, and as long as the loading is applied from time t1 to t2, it will maintain its position or deformation, and once the loading is removed at time t2, it will go back to its initial position. This is the elastic material definition as a property. On the other hand, viscous material, if we apply a loading from time t1 to t2, the material will respond, but with time. It will take time to respond. And once the loading is removed at time t2, it will not recover, so it will maintain its deformation. Bitumen, the main controlling the behavior element in the asphalt, is a viscoelastic material, which means it combines both the properties of the viscous and the elastic materials. So typically, in ambient temperature and normal frequency of loading, if we apply a load at time t1 to t2 and then remove the load, the response would be at the beginning initial elastic and instantaneous response due to the elastic property, as well as a deformation with time due to the viscous property. Once the loading is removed and within the unloading phase, part of the deformation will be recovered due to the elastic property, and part of it will not be recovered due to the viscous property. Well, bitumen, being viscous or elastic, depends on two parameters, which are the temperature and the loading frequency or the speed. It is more of an elastic material at very low temperature and high frequencies, and more of a viscous material at high temperature and low frequency of the loading. So if we look at the graph below, the solid line shows basically what is the performance within the loading frequency and temperature, and this can be divided into three regions. The first region to the left, where the temperature is very low and the frequency is very high, the material becomes very stiff, something like a glass, which basically more susceptible to cracking. On the other extreme, on the right hand, when the temperature is very high and the frequency of the loading or the speed is very low, the material becomes more of a viscous material, which means that it is more susceptible to soft or rotting. Between the two extremes, the material is a viscoelastic material. So depending on the temperature and the loading frequency, the behavior changes between viscous to elastic and viscoelastic property. How can we change this property? Is by applying a polymer modified bitumen rather than pure bitumen. And basically, this is the change. At the left hand, where the material becomes less stiff, i.e. less susceptible to cracking. While on the other extreme, on the right hand, where the rotting is more dominant, the material needs to be more stiff or less soft, and this is where the function of the polymer modified bitumen comes. So polymer modified binder or bitumens are prepared from mixtures of polymers, additives, and bitumen selected to achieve the required properties. Bitumen modifiers varies in type, and a considerable number of research have already experimented with modified bitumen, adding special fillers, fibers, and rubbers. Today, we're going to focus on polymer modified bitumen, i.e. the polymers, and the most common types are the elastomers and the plastomers. So what are the elastomers? Elastomers can be natural or synthetic rubber. They gain their strength from the physical cross-linking of the molecules into 3D network. They have a very high elastic response, and they are very good in resisting rotting, fatigue, cracking, thermal cracking, and aging. The most common types are SBS, PBD, and SBR. Among these, SBS is the most common used for the asphalt mixture. The limitation includes that some of them will be incompatible with some bitumen, they're relatively higher in cost, and there are some storage issues with some of them. The second most common type is the plastomers, which are rigid 3 network. They initially have very high strength or stiffness, but with the repetition of the load, they might fracture. They have very good stability in terms of storage and relatively lower cost than the elastomers. The most common types are EVE, EMA, and AAP. Among those, EVE is the most common used in the asphalt industry. Limitations include that the elastic recovery is not great as the elastomers, and the improvement in the low temperature is not great with the elastomers. So how can we know if the polymer improves the properties of the bitumen or the asphalt? To do this, there are already some standard tests on the bitumen and on the asphalt mixture that we can compare between a normal bitumen without modification and a modified polymer modified bitumen. The first one is the penetration test. it's within the EN 1427 standard, where a standard needle is allowed to freely penetrate vertically into a bitumen sample at 25 degrees Celsius for 5 seconds. The more penetration in the bitumen is an indication for a softer type. The second one is the softening point, again available in EN 1427. Softening point is defined as the temperature at which a bitumen sample can no longer support the weight of a 3.5 gram steel ball. Basically, two horizontal discs of bitumen cast in shouldered brass ring are heated at a controlled rate in a liquid bath, while each supports a steel ball. The softening point is reported as the mean of the temperatures at which the two discs soften enough to allow each ball enveloped in bitumen to fall a distance of 25 millimeters. So the test is an indicative of the tendency of the material to flow at elevated temperature encountered in service. So how does the polymer SBS, which is elastomer type or EVA, change the behavior of the penetration and softening point? The left hand, as can be seen with the orange indicating the change of the SBS with the increase of the concentration of the SBS within the bitumen. So as the concentration increases, the penetration becomes less, meaning that the material becomes more stiff, and there is a gradual decrease in the penetration with increasing the concentration of the SBS within the bitumen. In terms of softening point, also the material changes the behavior, and there is an increase in the softening point, meaning that the temperature required would be higher. However, with the SBS material, it can be noticed that from around 5% to above, there is a sudden increase in the required softening point temperature, and this is due to the formation of the 3D structure between around 5% and above. For the plastomer type, EVE, again the same trend is observed, gradual decrease in the penetration and gradual increase in the softening point. However, plastomers such as EVE, they tend to influence the penetration more than the softening point, opposite to the elastomer as has been demonstrated for the SBS. The third type of testing is the DSR, the dynamic shear rheometer. And the first test done with the DSR is the frequency sweep covered in EN 14770. So this test, a bitumen sample is sandwiched between two plates. The lower plate is fixed during the test, while the upper plate rotates clockwise and anti-clockwise in different frequencies and different temperatures. For the frequency sweep test, typically the temperature range is between 5 to 45 with the 8 millimeter diameter plate, and from 35 to 85 degrees with the 25 millimeter diameter plate. The strain is usually limited to around 5% not to be involved within the nonlinear behavior, while the frequency change at each temperature from 0.1 to 10 Hz. So basically, one cycle, the material is exposed to shear stresses by moving, as can be seen, point A from point B to point C and then back to the middle, which is known as one cycle. Typical results can be seen now, where the G star is an indication of the stiffness of the bitumen. Master curve is a curve constructed from the results of the test, and it shows the change of the stiffness with the frequency, and embedded inside is the temperature. The graph here shows different polymer types and an average 40, 60, or 50 pen virgin bitumen. As we said, there are two deterioration mechanisms on the asphalt: cracking and rotting. So these are observed now on the graph. On the left hand, where the frequency is low and the temperature is very high, we acquire or need a higher G star, higher stiffness, so the material can resist the rotting. And as can be seen, normally or usually, the polymer modified bitumen different types colored here in the graph are higher than the black average 50 pen. On the other hand, on the cracking zone on the right hand, where we actually want a lower stiffness because the material become very stiff, and as can be seen, most of the polymer modified bitumen has a lower G star values than the average 40, 60, or 50 pen. However, some of them still on the same region or the same level as 50 pen. Moving on, the second parameter or result can be obtained from the DSR is the face angle, which is an indication how much elastic is the material. A lower face angle value is always required. The most important part here is when the material is exposed to rotting, it can or loading, it can recover quickly and by being more of elastic. So a 90 degrees of face angle means that the material is totally viscous. 45 degrees is a viscoelastic, and lower than 45 is more of an elastic material. If we have a look on the graph here, on the left hand zone is the most concerned part for the face angle. The average 40, 60, or 50 pen shows almost 90 degrees, which means that the material is more of a viscous. And this region is where the frequency is low and or high, the temperature is very high. While the polymer modified bitumen shows an improvement where the face angle actually reduced lower than the 40, 60 material, which means that the material is more elastic than the pure bitumen 50 pen. The second type of test also applied on the DSR known as the multiple stress creep recovery test. In this test, the upper blade is usually fixed and the lower blade is fixed while the upper blade rotates only in one direction, where the loading is applied for 1 second and the material is unloaded for 9 seconds. And this is for one cycle. So one cycle consists of 1 second loading and 9 second unloading. And the test runs for 10 cycles. Typical results can be shown here. This from one test where the blue one shows that at the peaks at the 1 second loading and continuously the material is recovering or partially recovering for the 9 second unloading for 10 cycles. Typical results at the end include how much is percentage recovery, and the test is applied at 2 stresses, 0.1 kPa, and after that 3.2 kPa shear stress. The graph below or the figure below shows the comparison between the polymer modified bitumen in the green and normal 40-60 for the penetration type bitumen. It can be seen that how much percentage recovery within the test, and the polymer modified bitumen type achieved around 70%, while the 50 pen less than 10%, and the test was performed at 60 degrees. So this shows clearly an improvement in the rotting resistance for the polymer modified bitumens in the bitumen scale. The other scale or the higher scale, the asphalt mixture, we have different tests can demonstrate this. And one of the tests that can be used is the 4-point bending test. Here, the specimen is restricted at 4 points by means of 4 clamps, The two outsider remain static, while the two inner clamps deflect according to the stress or the strain applied. This test simulates very well a pavement fatigue failure under traffic loading, because repeated loading causes the tension in the bottom zone of the specimen. Cracking will initiate and then propagate to the top zone until failure, which is the fracture usually occurs in the area of constant maximum value bending moment between the two inner clamps. Fatigue failure here is the moment at which the stiffness has decreased to half of its initial value. Typical result for this can be demonstrated here in this figure, where the number of cycles to failure against the strain shows that typically for a 50 pen asphalt mixture compared with a polymer modified mixture, and it can be clearly seen for the number of cycles, the polymer modified bitumen asphalt mixture requires around 200 times better than 200 times the number of cycles to reach the same level of strain as the 50 pen asphalt mixture, which is a huge improvement in the fatigue cracking resistance. There are other things that can be covered for the asphalt mixture, like rotting, fuel resistance, and there are already some tests already we have taken and proven that the mixture can be improved in rotting and fuel resistance in terms of polymer modified bitumen. The question that we need to raise actually, is the polymer modified bitumen suitable for all situations? As discussed, there are different types and different modifications, including polymer, fibers, and others. We need to ask the question whether the polymer modified bitumen is effective for this job by means of cost. Is the polymer available? Does it achieve workability and compatibility with the bitumen? We need to know exactly how much concentration we need to add, because this will affect hugely the property at the end of the asphalt mixture. Also, within the design, we know that some materials will have different types of bitumen. For instance, EME2, it has a 15 pen pure bitumen, which is harder than actually polymer modified bitumen, and this will affect the stiffness of the design. And finally, aging. Aging will cannot be avoided and should be considered. How will this polymer modified bitumen perform with aging? I'll leave this to you, and thank you for listening.